once we go through it, you'll be able to kind of make a little bit of sense of it. But you know, this is pretty much Unit 3 material, right? It's, if you have a look, what you're dealing with is a carboxylic acid anhydride, just one of those acid derivatives, and we're throwing an amine at it, nucleophile. So in the first step of all of these nucleophilic substitution mechanisms, the nucleophile attacks the acid derivative, right? So that's what you see shown here, the arrows to illustrate that, as the nucleophile is going to attack the carbonyl of the derivative, in this case the anhydride. And so if you follow those arrows through, what you would get as an intermediate is going to look like and I'm going to start just abbreviating that benzene ring as a pH because it's just getting a little bit hard to draw everything. So at this point, because the nitrogen now has 4 bonds, it would be positively charged. And so what I'm going to do right now is just do kind of a minus H plus step and get things mostly back to neutral. All right, so the nucleophile has added in. So if you think back to the nucleophilic substitution mechanism, what happens next? Yeah, you reform the carbonyl and kick out the leaving group, right? In this case, because we're dealing with an anhydride, the leaving group is a carboxylate. Right, so we're going to reform the carbonyl and kick out the leaving group. That's going to open up the ring. That's your intermediate product. All right, so it was a simple 2-step nucleophilic substitution on an acid anhydride. So in the second half of the mechanism, it says you're going to take this and add to it the acetyl chloride. So the acetyl chloride, if you think about it, this is an acid halide, and that is the most reactive electrophile we have in these mechanisms. So this is going to have to act as your electrophile. What is going to attack it in this? Yeah, the carboxylate's the only real nucleophile you have here, or the best nucleophile you have anyway. And so, this is just going to undergo another nucleophilic substitution with the carboxylate now as nucleophile. So all I did was have the O- of the carboxylate go and attack the carbonyl of the acid halide. And so we get an intermediate like this. This is our another tetrahedral intermediate. And so that was step 1 of a nucleophilic substitution mechanism. Step 2 is always reform the carbonyl and kick out the leaving group. So that's what I'm going to do now. Reform the carbonyl and kick out the halide leaving group. What kind of functional group have I just made? Another anhydride. So we have an anhydride here. You have a potential nucleophile there in the form of a nitrogen. And you know, if you think about what we're trying to make a heterocyclic ring with a nitrogen involved. So if you look at where we are, we're almost there. Right? All we really need to do, if that nitrogen were to act as nucleophile to attack the anhydride, you could go ahead and just do a minus H plus step, which I'm going to skip here in the interest of time. Oops. So the nucleophile attacked the carbonyl of the anhydride, and in the second step, as in the previous steps, you reform the carbonyl and kick out the leaving group. So in the end, you end up with that. So really, if you kind of break down the mechanism and think about it, it was really nothing more than 3 separate nucleophilic substitution steps. All right. Any questions on this one? So when you're doing your mechanisms, try to think of them in the broader context. You know, we typically will learn in these units kind of more or less one overarching mechanistic style. You know, back in Unit 2 it was the nucleophilic addition reaction. Here it's the nucleophilic substitution mechanism.
I have a question about the step where our nitrogen attacks the anhydride.
Mm-hmm.
Couldn't it just as easily attack the other carbonyl?
It could, yeah.
You'd get a mix, wouldn't you?
Well, maybe in theory. I mean, if it attack, you're talking about have the nitrogen attack over here.
Yeah.
Yeah, I mean that theoretically it could happen, but think about what the rings. That would just be kind of acylating this. Really. Yeah, I mean, I guess it could. It'd be a little bit weird, but you really kind of can disregard that because you know what you're trying to get to.
Okay.
Right? But that's the nice part about mechanism problems is you know what the answer is. You just have to show how you get to the answer. And so because I know I'm trying to get that, I don't even have to worry about the potential of it going over there because that's not going to give me what you're trying to get.
Okay.
But yeah, I mean, theoretically it could happen. It's not going to give you a stable of a product as this type of thing, but it could. Okay, well why don't we take about a 10-minute break and